Good afternoon to you all. I am Satya Kumar, Chief Executive, Heavy Water Board. And my presentation flow will be like this. First, I will discuss about heavy water technologies, then non-nuclear applications of heavy water, then diversified activities being taken up by Heavy Water Board, and we are taking up many new developmental activities that I will discuss at the later part of my presentation. Homi Bhabha envisioned in 1948 that government should explore immediately the possibility of utilizing cheap hydroelectric power in India for manufacturing heavy water on one hand, and export heavy water to various countries. And I have pleasure to inform you that we not only produced heavy water to meet the domestic requirement, and also we are exporting to many countries, earning foreign exchange in millions of dollars. For the people who are not aware of what is heavy water, this is the slide which shows that heavy water is stable, it is non-radioactive, non-toxic. It is used as coolant and moderator in PHWRs, and also nowadays heavy water is used in many non-nuclear applications. We will discuss about these things in detail about non-nuclear applications of heavy water in the later part of presentation. There are three stages, as you all know, three stages of nuclear power program in India, and the Heavy Water Board. Input from Heavy Water Board is heavy water, solvents, and enriched boron, beaten enriched boron carbide pellets, and also nuclear grade sodium. In similar way, Heavy Water Board has also got three phases, as Verma Sahib has told. Initial stage is that heavy water should be produced at any cost, and next phase is heavy water at least cost, and third phase is we also produce heavy water. As Mahapatra Sahib has told, we are into many activities which I will discuss in detail later. And in India, we have mastered 4 technologies for production of heavy water. First one is electrolysis, followed by cryogenic distillation of hydrogen. Second one is ammonia hydrogen monothermal process. Third one is ammonia hydrogen bithermal process, and H2H2O bithermal process. And later we have mastered ammonia hydrogen technology also. This heavy water journey in India, modest journey, has started in 1962 with setting up of heavy water production plant at Nangal. Actually, when Bakra Nangal project was constructed, cheap electricity was available. At the time, unit cost of electricity used to be around 30 paise to 40 paise, and there were no consumers. Surplus electricity was available. Then Baba told the then Prime Minister of India that India needs heavy water, and we should utilize this surplus electricity for production of heavy water using electrolysis of heavy water followed by cryogenic distillation of hydrogen. First drop of heavy water in India was produced on August 9, 1962, and later this process was modified, and this was connected with fertilizer plant, and that syngas used to be supplied from fertilizer plant, and deuterium concentration in syngas came down, and also electricity cost has increased, and this process has become unviable. Hence, these plants were decommissioned in August 2002. Second technology, as I have told, this is H2SH2O based technology. Raw material for this process is water. Normal water contains around 152 ppm of deuterium, and this process is a 3-stage cascade. We enrich deuterium from 152 ppm in water to around 15%. in exchange unit where we use, as Verma Sahib has told, we handle highly toxic hydrogen sulfide gas. Toxicity is such that at 800 ppm, it is instantaneous death. So many, because first time we were handling H2S in India for production of heavy water, and we started from scratch. It was very difficult, and many studies were carried out in BRC for development of this technology. And also, this is corrosive also. H2S, moist H2S is highly corrosive. So material selection was very difficult, and it is highly corrosive to carbon steel. And protective film formation, that process was developed in BRC, and we have carried out, and protective film were formed. And as we are handling toxic H2S gas, many inbuilt safety features are there to take care of any eventualities. And we have got around 126 meter height flare stack to take care of intentional and unintentional releases of H2S gas. And designing 126 meters height flare stack in those days, in 1980s, when computers were not there, and doing risk analysis, you can imagine it is very difficult task, and it was done. And this plant was commissioned. First plant was commissioned at Kota, and subsequently, with the experience gained from Kota, many modifications have been carried out, and second plant was set up based on this technology at Manuguru. At Manuguru, we have got 2 streams of H2S, H2O based plant, and Kota, we have got 1 stream. In this, as I have told you, this deuterium gets enriched in 3-stage cascade from 152 ppm to 15%. Further enrichment is carried out in vacuum distillation tower, and this technology was totally developed in BRC. From 15% to nuclear grade enrichment, 99.984 plus percentage is done in vacuum distillation unit. And second technology what we have mastered is ammonia hydrogen isotopic exchange process. This in this process what we do is we take it is integrated with fertilizer plant. It is parasitic. It depends for its feed from fertilizer plant. Syngas we take from fertilizer plant, and it contains around 115 ppm of deuterium, and it is enriched in 2-stage cascade here. Up to 30%, and then further enrichment is done in vacuum distillation unit. Here also we faced a lot of difficulties with respect to ammonia converter as well as ammonia cracking unit is there. This for cracker we require a special catalyst, because cracker is operated in heavy water plants at very high pressure and high temperatures. It is operated around 145 kg pressure and at 600 degrees centigrade. So for to meet these conditions, to tolerate these conditions, special catalyst is required. And nowadays we have indigenized this catalyst also. Earlier we were getting this catalyst from Halder Topsoe. Now we have indigenized this catalyst with the company in India, Sudchemy company. This heavy water, because the natural abundance of deuterium is very low, as if you see water as well as syngas, raw materials which are used for heavy water production technologies, it is highly energy intensive process to recover deuterium from such a low concentration and enriching up to nuclear grade. It takes a lot of energy. They are highly energy intensive processes. Approximately H2S, H2O based technology consumes around 30 gigajoules per kg of heavy water, whereas this process consumes around 24 to 25 gigajoules per kg. But it is parasitic. If any disturbance are there in fertilizer plant, it disturbs our heavy water plants also. And once it gets disturbed, it takes around 15 days to get the product again. Whereas H2S, H2O based technology, it is independent, and we can come back to production within 72 hours. That is the advantage of H2S, H2O process. Disadvantage is, as I have told you, we have to handle highly toxic hydrogen sulfide gas. This evolution of heavy water program in India, it started with Nangal, as I have told you, 1962, and then we had one plant at Baroda. This is based on monothermal ammonia hydrogen process. It was commissioned in 1977, and then Tuticorin, it is also monothermal based ammonia hydrogen exchange. It is integrated with SPIC. In Baroda, it is integrated with GSFC. And Tuticorin plant, and then 1985 we have got two plant commissioned, that is one at Kota based on H2SH2O technology, and Talcher we have got a bithermal ammonia hydrogen exchange process. It is integrated with FCI, Fertilizer Corporation of India Fertilizer Plant. And at 1987 we have commissioned Thal heavy water plant. It is, we take raw material syngas from RCF, whereas in 1991, Hazira plant was commissioned and it is integrated with Kripco, and Manuguru, it is based on H2SH2O technology. And later 1994, that heavy water plant Baroda was decommissioned because the fertilizer plant has modified their technology, and that the pressure required for heavy water plant operation, they have brought it down. Actually, fertilizer plant, after doing the technology modifications, the pressure has come down, and we could not operate Baroda plant. It was decommissioned, and Tuticorin has gone for shutdown in 2007 because PIC was shut down because of non-availability of naphtha. But they have restarted their SPIC plant in 2015, and we are in the process of refurbishing our heavy water plant. We will be starting heavy water plant at Tuticorin in the next year, June. We will be commissioning the plant again. In Gujarat, we have got Baroda heavy water plant. And in addition to heavy water, when plant was decommissioned, we have gone for diversified activities at Baroda. We have got TBP plant, tributyl phosphate solvent we produce, and also we are into production of nuclear grade sodium. And we have got one more plant in Gujarat, that is a heavy water plant Hazira. And the central office we have got in Mumbai. And we have got one more technology demonstration plant in RCF Chembur, where we carry out many developmental activities, and we have got one more plant at Thal, heavy water plant Thal. And Kota, we have got heavy water plant, Rajasthan, and in Talcher, we have got heavy water plant. It was decommissioned because of shutdown of FCI, and we have gone to diversified activities at Talcher. We produce boron enrichment plant we have got, and we have got TBP, and also we have got VSPP, and where we produce various solvents. At Manuguru, in addition to heavy water plant, we have got boron enrichment plant. Again, this is based on ion exchange chromatography technology, and we have got elemental boron plant also. At Tuticorin, when heavy water plant was shut down, we have gone for versatile solvent production plants, where we produce various nuclear grade solvents. Present status of heavy water technologies, if you see, India is the largest producer of heavy water, and it is the only country which uses multiple technologies for heavy water production, and these technologies are fully matured and robust. They are very much energy efficient and environmental friendly. We have carried out many energy conservation measures in both ammonia-based heavy water plants as well as H2S-based heavy water plants. Once upon a time, when we started in 1990s, the specific energy consumption used to be around 47 gigajoules per kg of heavy water. We have brought it down to 30 gigajoules by carrying out various modifications. For for resource conservation also, we have carried out many modifications at both at plants based on H2SH2O based technology and also as ammonia based technologies. For example, I will tell you this, at Manuguru, we used to consume around 5,500 tons per hour of water. With modifications, we have brought it down to nowadays it is operating at 1,750 tons per hour. We have, India is self-reliant with respect to heavy water. We have mastered various technologies, and we have met the mandate of supplying heavy water for Indian nuclear power program, and with minimal specific energy and with minimal resource consumption and excellent productivity, safety and environmental performance, fulfilling present demand of all operating PHWs in India and also meeting global demand. Actually, nowadays, this non-nuclear applications of heavy water, we will be discussing that in detail later. Non-nuclear applications of heavy water have increased a lot, and we are meeting global demand. We are exporting to many countries, and we are geared up. We have analyzed the supply-demand scenario up to 2037, and we can meet the requirement of heavy water for the upcoming 15 PHW years. And the capacity augmentation also we are planning. We are planning to have third stream at heavy water plant Manuguru. This is the specific energy consumption. If you can see, as I told you, it started with 45 gigajoules. Overall performance of heavy water board, it used to be around 44.7 gigajoules per kg. It has come down to around 30 gigajoules per kg over the years. And we also support Atmanirbhar campaign as far as heavy water is concerned. We have signed agreements with various companies in India, ClearSynth and Sinmar. In 2018, we supply heavy water at concession to Indian parties. Recently, Merck Life Sciences Sigma Aldrich Bengaluru has entered into long-term agreement for 5 years for supply of heavy water. We will be earning around 1,000 crores of rupees with this agreement. And they have set up their facility in Bengaluru. And we are committed to boost the domestic production of jewelry-related compounds. This heavy water is used for production of jewelry-related compounds. Global imprint, if you see, there is, as I have told you, surge in demand of heavy water globally, as many non-nuclear applications of heavy water is being harnessed commercially. During last year, export to advanced countries like USA, France, Republic of Korea, Japan, Germany, and hundreds of metric tons of heavy water has been exported, generating foreign revenue millions of US dollars. These are the countries where we are exporting nowadays. And recently we have received inquiries from Argentina also for their nuclear applications, means for their reactor makeup requirement. We are considering that. And also we have received export demand from Russia, from Rosatom Russia, for non-nuclear applications. This deuterium, as I have told you, applications have increased tremendously over the last few years. It is, in addition to nuclear reactors, it is used in life sciences, it is used in analytical sciences as deuterated NMR solvents, and it is being used in electronic components like OLED TVs, TV screens, and also is being used in information technology for OFC cables. And many more applications are there nowadays. Recently, there is a demand for heavy water for production of eye drops. It is used in child myopia, for rectification of child myopia. They require heavy water. Heavy water is being used for the eye drops. Now we will discuss about non-nuclear applications of heavy water. This is heavy water is used for the manufacture of drugs also. And first drug was approved by FDA in 2017. It is what is the advantage of using heavy water for production of drugs? If you see, it is more stable and reduce drug-drug interaction. Actually, if you see, if you replace hydrogen atom with deuterium, what happens is CH bond and CD bond. If you compare CD bond, that bond strength is high as compared to CH bond. So it takes more energy for disintegration of this bond. So it the increased lifetime of the drug increases tremendously, and lower dose requirement if you use heavy water for the manufacture of drugs, and there is no change in biological properties of drugs, and it has got less side effects. Toxicology with respect to drug, if you use heavy water, the toxic effects come down. So far, as I have told you, 2 deuterated drugs have been approved by FDA, and deuterated drugs in pipeline. 3 drugs are under third phase clinical trials. 4 drugs are under preclinical trials. Actually, yesterday I was going through Science Journal in October 2023. A Science Journal, it was reported that 16 drugs, deuterated drugs, are under pipeline. Life sciences usage of heavy water. In life sciences, it improves the thermal stabilization of biomaterial. It is used for polio vaccine also. Heavy water is used for increasing the thermal stabilization. And short-term safe storage of biomaterial, heavy water is used. And therapeutic applications also, heavy water is used. Heavy water in collaboration with EVRC demonstrated thermostabilization of oral polio vaccine D2O, obviating the cold chain. Heavy water is also used for solvent in a number of applications, nuclear magnetic resonance applications. These are the solvents which normally be used for NMR spectroscopy, that is dichloroform, DMSO D6, acetone D6, acetonitrile D3, and benzene D6. Deuterium is also used in manufacture of OFC cables. Establish the facility for generation of deuterium gas. We have got this facility at Baroda. We can manufacture deuterium gas, and it is used, as I have told you, low water peak optical fiber. We are supplying to leading optical fiber manufacturer in the country. OLED industry, deuterium gas is used. This helps for thinner displays. Displays are more flexible, a slower rate of chemical degradation, and longer device lifetime, improves overall performance and quality of OLED. As you all know, the components which emit blue light, they have got higher frequency, so degradation is faster. If you use deuterium for the manufacture of those deuterium gas for manufacture of the components by replacing H with D, what happens is its lifetime increases by 6 to 10 fold. And heavy water, what are the diversified activities heavy water board is contemplating? We will be discussing now. We are also producing beaten-enriched boron for the second stage nuclear power program. It is used in FBRs, and production of solvents, nuclear hydrometallurgy, and establishing technology for RM recovery from phosphoric acid. Actually, we have got a plant at TDP in RCF Chembur, where we used to extract RM, rare material, from phosphoric acid, because RCF has got a phosphoric acid plant for production of phosphatic fertilizers. So we used to take phosphoric acid from RCF and extract rare material from them, and we have demonstrated this technology, and we have produced around 16 tons of rare material, which we have supplied to IREL. And also for societal initiatives, we have set up a plant at oxygenating water plant at Maduguru pilot scale facility, and we have also into the production of deuterium depleted water. Actually, while producing heavy water, this comes out as a byproduct, around 125 ppm deuterium depleted water. As I have told you, normal water contains 152 ppm. Whereas this deuterium depleted water, which comes out as byproduct while manufacturing heavy water, it is around 125 ppm, but we can produce up to 10 ppm deuterium depleted water also. We are supplying to many parties in the country. And we have got closest technology for nuclear grade sodium production, and we have developed ARIC, asymmetric rotating impeller column, which reduces the footprint area required for mixer settlers, solvent extraction technology. And we are into cryotechnology also, solvent extraction for industrial deployment, non-nuclear applications of heavy water, And new technologies we are contemplating, cobalt, gallium, hydrogen, helium, polysilicon. We'll be coming these topics later. And boron carbide for FBRs. We have established two technology for boron beaten enrichment. One is ion exchange chromatography. That plant we have set up at Manuguru. And second one is BF3 ether complex distillation for enriching beaten isotope. We can produce beaten enriched B4C pellet 65 greater than 65% as required for CSR and DSR and FBRs. And as poison and control at 50% B10 and 90% B10 for FBTR. And in fact, we have supplied 50% B10 B4C to FBTR for making it 40 megawatt thermal. No, we have supplied, that was loaded into the reactor. And production process mainly involves beaten enrichment using exchange distillation of BF3 ether complex, conversion of BF3 to KBF4, and then later electrowinning to produce B4C boron, and then boron carbide pelletization using pyrometallurgical processes. Heavy water board, as I have told you, B4C pellets FBTR, which was required for attaining its design power capacity of 40 megawatt thermal in March 2022. And we have also got a BF3 gas production facility at Talcher, and which finds applications in neutron detectors. This is the production cycle: boron exchange distillation for beaten enrichment, then KBF4 conversion. This is done at Talcher. Later, we do electrowinning at Manuguru and powder purification, afterwards conversion to B4C pellets. Then we supply to NFC for fabrication of control rods. This is the facility available at, this is the distillation column. This is available at Talcher, and this facility is available at Manuguru. This is the electrowinning cell. Then rare material recovery from secondary sources, as I told you, demonstrated this technology for recovery of rare material from wet phosphoric acid at Technology Demonstration Plant RCF Chemburu, and RM is produced and supplied to IREL. And we are going to scale it up, and we are going to set up industrial scale facility at heavy water plant Tuticorin. NMR solvent, deuterated NMR solvents, we have got plant at Baroda, where we produce dichloroform, acetone D6, DMSO D6, acetonitrile D3, and benzene D6. These are used for NMR spectroscopy. And we are marketing it through BRIT Mumbai. As I have told you, deuterium depleted water also we produce. We have got, as I have told you in a quota, for upgradation to nuclear grade from 15%. It is done through vacuum distillation unit. We have, that is 5-stage cascade, tray columns were available at Tuticorin. We have replaced that with packed tower. So 2 columns were available as spare, and we used that columns and produced this DDW of 10 ppm. And reported to beneficial, it is reported to beneficial in cancer therapy, and we are having collaborative R&D with the Tata Memorial Hospital to establish anti-cancer potential. Actually, many research papers are there which show that it is useful as anti-cancer potential. And preliminary results they are encouraging, very encouraging. This is also used for diabetic metabolic disorders, and also it is used as anti-aging agent as per the research available in the literature. And USA, Japan, Russia are already prescribing DW as adjuvant therapy to eliminate side effects of chemotherapy, and also to increase drug efficacy in the presence of deuterium depleted environment. These are already available in the market, and recently we have given it to 3 firms in India. They are also launched their product. Next, Heavy Water Board has taken up activities O18 water, H2O18 water, healthcare initiative by Heavy Water Board. This is 95% H2O18 PET scan for cancer detection, and 10% D2O18 for metabolic studies. Heavy Water Board has set up a pilot scale facility at Manuguru, and product quality is better than imported H2O18 water, and industry scale facility we are planning to set up at Manuguru. Actually, we have carried out experiments, initial experiments at Tuticorin using a small column. Based on that bench scale studies, we have set up pilot scale facility at Manuguru, and we have withdrawn the product H2O18 of 97, greater than 97%, and it was tested on patients, and PET scanning, that images are perfect. And we have got the sample analyzed in USA, and it is better than what is being imported by India. Actually, the cost of this 1 liter of H2O18 water is around 18 to 19 lakhs, and we will be substituting the import with our product, and we are in talks with RMC as well as BRIT for supplying this H2O18 water. What are the engineering challenges we have faced for H2O18 water enrichment? It is separation factor is very low. You can see it is 1.006, and low liquid flow measurements and control. Flow varies from 1.8 kg per hour to 0.003 kg per hour. Handling such a flow at such very low rates, it is very challenging. And pumps for such low interstage flow transfers, and column sizes, it is varies from 20 inch to 1 inch. It is actually 11 stage cascade what we are having at Manuguru for enriching. Actually, when you enrich deuterium from 152 ppm to nuclear grade, O18 water also, O18 natural abundance is 0.2%. It also gets enriched up to 0.4% along with deuterium. From 0.4% becomes the feed for this unit, O18 water, O18 production facility, and we are enriching from 0.4% to 97, more than 97% in these columns, 11 stage cascade. And main challenge is inventory reduction of inventories by doing process intensification. It is a very big challenge because inventory should be as low as possible, as we all know. And development of electrolyzer for production of high purity oxygen. Actually, what we do is, what we produce is D2O18, that is called as double D labeled water, DLW. That we split D2O18 into D2 and O18, and then we split normal water H2 and O16 into then we combine H2 and O18 in a recombination unit to produce H2O18. These are the special equipment that are employed for enrichment of O18 water. We have got low flow gas recirculator, DX packing we have used, and low flow diaphragm pumps. These are special equipment what we have used for O18 enrichment. These are the facility available at Manuguru. This is the flow sheet, 11 stage cascade, and this is the columns, 11 stage cascade columns are enclosed in this, and then we have got the recombination unit for recombining H2 and O18. Next one what we are into is nuclear solvents. We produce all these solvents, DEFA at Talcher, TBP, tributyl phosphate at Talcher and Baroda, TOPO, TAPO, TAAP, Doha, and DEFA2 at Tuticorin. These solvents are used in nuclear hydrometallurgical processes, and these solvents were being imported earlier. Then Heavy Water Board took the challenge and we produced these solvents, and we are meeting the demands from the Indian Nuclear Power Program. Were being imported earlier, and the solvents supplied to these solvents we are supplying to NFC, BRC, IREL, CARP and IGCAR, and Heavy Water Board made the country self-reliant with respect to nuclear solvents. Then we also produce potassium metal at Baroda. We have got a plant having capacity of 22 metric ton per annum, and this potassium metal is used for as catalyst in ammonia hydrogen based process, potassium amide catalyst for production of potassium iodide catalyst, we use potassium that is being produced at Baroda. In-house consumption is being met through this plant. We have got one nuclear grade sodium metal also we produce. It is used as coolant in BRs. Electrolysis of molten salt in down cells. We are using down cell for production of sodium. Actually, we have carried out experiments on 2 kiloamp cell, and we have produced around 6 tons of nuclear grade sodium, which we have supplied to IGCAR. And now we are scaling up to 24 kiloamp cell. That cell has been operated and some problems were there. We are modifying the cell. We will be starting shortly. Within 3-4 months, we will be testing that prototype cell, 24 kiloamp prototype cell. And next is the new development activities being taken up. This is the last topic I will be discussing about. This is development activities Heavy Water Board is doing. Yeah. Actually, Midhani, while preparing the strategic components, they develop, they generate scrap, miraging steel scrap, MDN 350, 250. This scrap contains cobalt, nickel, and molybdenum. For recovery of this valuable metals from this scrap, technology has been developed by BRC, and we have tested this technology on bench scale at technology demonstration plant Chemburu, and we are planning to set up a 5 ton per annum plant at TDP to meet the requirement of IREL. IREL has already set up a permanent magnet plant, samarium cobalt permanent magnet plant at BRC Vizag. For that, they require around 2 tons per annum cobalt. Now cobalt is being imported now, so we will be meeting that requirement by setting up this plant at TDP. This is the flow sheet. This is solvent extraction technology. Actually, whatever equipment is available at technology demonstration plant, that we will be using for extraction of cobalt, molybdenum, nickel from this scrap. This is the cycle. Actually, scrap comes in the form of briquettes, and then we leach out the impurities, and then we produce, after solvent extraction, we will be producing nickel sulfate and cobalt sulfate, and then we will be converting into nickel oxalate and cobalt oxalate. After that, pyrometallurgical process, we will be producing cobalt pellets, cobalt and nickel pellets. One more project what we have development acted, what we have taken up is gallium extraction. Gallium actually, India imports whatever gallium requirement of India is met through imports only. This is a strategic metal. This is used in electronic industries, as used in semiconductors, LED, solar cells. And in nuclear industry, gallium is used as alloying element with strategic material for phase stabilization of plutonium. And there are no primary source of gallium. Natural abundance is only 20 to 80 ppm in bauxite ores. Gallium gets concentrated, while in aluminum industry it gets concentrated to 100 ppm in Beer's liquor. That which we want to extract. This is the ion exchange process. This process is developed by BRC again in lab scale, and we have tested this process at bench scale in TDP, and we were successful. And demonstration scale facility is being set up at NALCO Damanjodi. Engineering is completed. We will be setting up one demonstration scale facility at Damanjodi. This is the gallium consumption pattern given by this Ministry of Mines, and integrated circuits and wireless we require around 67%. Optoelectronics 31% is used, and special alloys around 2% is used. Gallium is used. All these met through imports only. Another project what Heavy Water Board has taken up is production of helium. Actually, this is purge gas in fertilizer industries. it gets enriched with respect to helium up to around 1.5%. That helium we want to recover. For that technology, technology has been finalized, and we will be using PSA followed by cryodistillation method, cryoadsorption method, and the plant will be set up, pilot scale plant will be set up at TDP. For that procurement process is going on. This is the process what we are thinking of. PSA, that nitrogen will be removed, and then hydrogen, argon, helium, which purge gas contains, goes to cryoadsorption unit, where we adsorb hydrogen and argon, and helium comes out as product. Grade A helium 5 and helium we will be planning to produce. Next project Heavy Water Board is taking up is IS process for hydrogen generation, iodine sulfur process. Technology is developed by BRC. This is thermochemical splitting of water. Only feed material is water only, remaining chemicals will be in closed loop. This metallic closed loop with design capacity of 150 NLPH, it was demonstrated successfully at BRC. Now mandate given to Heavy Water Board is to set up 3000 NLPH demonstration facility at TDP Mumbai, that now resigned as a Heavy Water Board facility Mumbai. This is the process what we follow for IS process. This is the Bunsen reaction, and then all the chemicals will be in closed loop. Only raw material is H2O. One more plant what we are envisaging is polysilicon plant at Heavy Water Plant Talcher. Technology is developed and established at BRC. We will be setting up around 5 tons per annum of polysilicon plant at Talcher. This process involves production of trichlorosilane TCS in floating bed reactors, and then distillation of TCS and then followed by CVD. This 5-stage distillation will be carried out, and then afterwards it will be deposited using chemical vapor deposition technique. And total engineering will be carried out by BRC. This is the process which we will be following at Heavy Water Plant Talcher. These are some of the technologies Heavy Water Board is taking. In addition to heavy water, Heavy Water Board is taking up all these activities for import substitution, and whatever new technologies are being developed by BRC, Heavy Water Board is ready to take up for scaling up. We have got expertise in scaling up of technologies. We are into multifold activities of, these are the multifold activities of Heavy Water Board. Thank you very much. If you have got any queries, you are free to ask.